second part of this chapter is talking about the valence bond theory, the second theory of bonding, and it focuses on the concept of hybridization. The meaning for hybridization means mix, right? So in this theory, we talk about the mix of atomic orbitals to provide bonding. So this theory explains that bonding is not as easy as we think. The orbitals first need to mix, and then they are prepared for bonding. It's not just like atoms approach and bonding happens. So first orbitals should be prepared. Let's focus on carbon, which is the central atom. If you look at this molecule, CH4, you drew it, you worked on the SCPR model for it, and now we are going to focus on its hybridization. When you look at this molecule, you see 4 equal bonds, right? There is no difference between any of these bonds. Now, look at the electron configuration of carbon. In order to form a bond, we must have a single electron, right? How many single electrons do you see in the electron configuration of carbon? Only 2, right? When you draw the orbital diagram. But you have 4 bonds, means you need to have 4 single electrons available. Is that correct? You need single electron to pair with the second electron from the other atom to form the covalent bond, right? Here, when you write the regular electron configuration of carbon, you just see 2 single electrons available. So you must have 4 electrons available. What happens? The theory is that electron from, we're talking about the valence level, right? Because the valence electrons in the outermost shell or valence shell are the ones that participate in bonding. So forget about the electrons in 1s, we just focus on valence electrons in the valence level. So, electron jumps from 2s to 2p, and look what happens. Then you will have 2s1, or if I want to draw the correct energy, it says 2s1, and energy of P is a little bit higher, right? I should have done the same thing before, excuse my drawing. Alright, now how many orbitals do you have with single electrons? This is 2p3. 4 electrons, right? But what you see, in order to form the completely equal bonds, the type of the orbitals must be the same, or like the orbitals that form the bond must be the same. But here you have an electron in 2s, which is a little bit lower, and you have 3 electrons in 2p, which are a little bit higher. So you remember S is the space of atom, which is spherical. P orbitals are dumbbell shaped, so not the shape, not the energy is the same. So what happens is that s orbital increases its energy, p orbital decreases its energy, and they become the same energy. We call it degeneration. They degenerate the orbitals. So what happens? At the end, you will have 4 orbitals, the same energy. Now, how to label them, how to name them? The orbitals came from an s orbital and 3 p orbitals, right? So 1s plus 3p makes sp3. So you have how many sp3 orbitals? 4. The number of hybrid, these are called hybrid orbitals, the number of hybrid orbitals is equal to sum of the atomic orbitals that made them. You had 1 s orbital and 3 p orbitals. What's the total? 4, and you will see 4 sp3 orbitals. So you call it sp3 hybridization on carbon. Now, we are expected to know what happened, how the hybrid orbitals formed, but I have a shortcut for you to, whenever you have the tests or exams and you want to be fast and determine the hybrid, how to determine it? Count the bonding and non-bonding. Never count double or triple bond, okay? One more time. Count bonding and non-bonding electron pairs, but do not count double and triple bonds, okay? So, how many bonds do you have here? Only 4 bonding pairs, right? The first one always is going for s. How many types of s orbitals do you have? 1. So, it always have s. The rest of them, how many maximum p orbitals do you have? 3, right? So if you have 4, the first one is for s, the rest for p. So the hybrid is sp3. You counted 4 groups. One of them is always for s, deduct 1 for s. So you have 4 groups. 1 is for s and 3 for p. So the hybrid is sp3. It's short and sweet, isn't it? So you count bonding and non-bonding electron pairs, subtract s, 1 s only, and the rest will be for p, or if you have more, we'll go to d. Okay. What if we have a double bond? I told you not to count the double bond, right? So if you ignore this double bond, how many bonding pairs do you have around each carbon? You have 2 carbons here, right? So how many bonding pairs do you have around each carbon? I count 1, 2, and 3, right? So seems like I need 3 electrons available, correct? So let's see what happens here at this level. Again, in the valence shell. 2. Then electron must jump. You have 2s1 again and 2p3. Okay, that's what's happening on every carbon, okay? Excuse me. So, now, we said we don't consider the double bond, right? So, how many bonds do we have besides the double bond? 3. 3 single bonds, right? So, we need only 3 of these electrons. We only need 3 electrons here. And again, I should have drawn S a little bit lower than P. Okay? Same here. I always forget, but I have it in my mind. Isn't it crazy? Alright, so we only need 1 electron in S and 2 in P because we are dealing with only 3 bonds. This bond, and this bond. Alright? So when they degenerate, we have these. So it's 1s and 2p, right? So the hybrid is sp2. 1s plus 2p gives you sp2. How many? 3, because 2 plus 1 is 3. Now, we have a leftover p orbital, right? We have a leftover p orbital. What to do with it? This leftover p orbital is the one that is going to create double bond. Okay? So, this p orbital is going to create double bond, And if you remember from last chapter, we had 3p orbitals in the x-axis, along the y-axis, along z-axis, right? So let's say this is pz along the z-axis. So if I want to draw this molecule, actually, I will draw it as here is the hybrid orbital. Oops, don't have enough space, so all right. These are 3 sp2 orbitals for each carbon. sp2, sp2. How many electrons in each? 1. sp2 here for this carbon. And for the second carbon, that's the same story. sp2, and we had 2 electrons in each. And I have to show them bigger because I need to show the electrons. This pen is not helping because it's too thick. All right. The same for this carbon. 1 and 1. sp2 and sp2. Now, the hydrogens can form bond. Hydrogen can form bond. And the same story here. 1 electron from each, right? So, Pz is left over on each carbon. This is Pz, and this is Pz. So, 1 in each, right? 1 electron in each. So, because the electrons move from top to bottom, so you show the overlap for both. 2 electrons, 1 here, 1 here, they have overlap. So they will create such a molecule. You see, this is the sigma bond. We call it sigma bond. You remember we said we call one of them sigma. So the orbitals, the bonds that are formed from hybridization of orbitals are called sigma. And leftover p orbitals will form pi. So one more time. Sigma bond is from hybrid orbitals. And pi bond is from leftover p orbitals. Oof. Okay. I hope you understood. Replay the video and review what I said about it. The difference between this molecule and the previous molecule is that we have a leftover p orbital. By the way, I forgot to draw the hybrid structure of this molecule. If you need to draw it, is carbon with the hybrid orbitals. 1, 2, 3, and 4. How many did we have? 4 sp3 orbitals. 1 electron in each. And then now, let me label them. You see, p orbitals are all used, so there is no leftover. And then we have 4 hydrogens. And that's how a bond forms. Okay? And at the end, let's add one more pi bond. So in this triple bond, there are 2 pi bonds. And this first one is sigma, right? So around each carbon, there are 2 sigma bonds. So make sure we just need 2 electrons. In the electron configuration of carbon, again, 1s2, 2s2, 2p1, energy. Let me try it correct way. All right, 2p2, I'm sorry. So again, electron jumps from 2s to 2p. We will have 2s1 only and 2p3. Okay, degeneration happens, and we will have, oh, how many of them do we need before the degeneration? How many of the orbitals do we need for hybridization to form sigma bonds? Only 2. So we will have only these 2. All right? And don't forget, this was along x-axis, this was along y-axis, and this was along z-axis. So after degeneration, we only need 1s and 1p. 1s plus 1p will form 2sp, right? So now we are going to have our 2p orbitals, py and pz. Okay? 2 leftover p orbitals. Now let's see what is the shape of the molecule. 2 carbons. These are the sp orbitals. sp, sp. 1 electron from each carbon. We need another sp orbital, right? Because we have 2 sp orbitals. The second one is on the other side of each carbon, sp and sp. So you see, you're showing the sigma bonds with sp. Now, hydrogens. 2 leftover p orbitals, right? So let me show them with different colors. Let's say this is py. How many electrons do you have in it? 1. And this is the py on this one. Right? You also have a pz. So there is overlap between py orbitals and also pz. This is the z-axis. And there's also. So your molecule will look like something like this. Sigma, py, and pz. So py and pz are not in the same plane of px, right? So pi bonds are not in the same, excuse me, pi bonds are not in the same plane of sigma bonds. That's why we say they don't have any role in the hybridization. So one more time, you want to determine the hybrid on this molecule. So you just write the electron configuration, do the jumping of electron, degenerate the orbitals. You don't consider the double and triple bond. So you just need 2 bonds, means 2 electrons, 2 p orbitals left over that will form the double and triple bond, the pi orbitals. But again, if you want to find out the hybrid in the shortcut way, 2 sigma bonds. One of them is for S always, and one of them is for P. So the hybrid will be SP. And I guess we forgot to determine it for this molecule. We have how many sigma bonds around each carbon? 3, right? 3 sigma. So we have 3 sigma, 1 for S, 2 for P. So the hybrid as we determined will be sp2 on each carbon. And here will be sp on each carbon. Please replay this video, try to work on other molecules, and let me know if you have any question.